Hi everyone, and welcome to what I think is one of the most fun and relatable chapters in all of physics. I really do feel like I've saved the best for last in a way by having our last week together, allowing us to study sound and waves. So let's start with the question of why we care, okay? Sound and waves have just an amazing number of applications in the medical field. For one, X-rays. X-rays are waves, okay? For two, ultrasounds. Two of the biggest ways that we actually do biomedical imaging of the body have to do with waves. And so for this why do we care slide, it says, assuming that the average molecular spacing in bone is about 5 nanometers, really small, really, really small, what is the maximum frequency that an X-ray could have such that it goes through muscle tissue but not a pelvic bone or a pair of medical scissors? And online, you can unfortunately find way too many images like this, where after a surgical procedure, something has been left behind. One of the big reasons why I did not decide to go into surgery is because I'm a very absent-minded person, and I would no doubt leave a pair of scissors or gloves inside of a person. Okay, but moving on from that. The most important fact that you need to know about waves, why are they so important? It's because they are the brilliant method that the universe has invented for transporting energy, okay? Waves, simply, if they have one job, that job is to move energy from one place to another, and that energy has a lot of possibilities, right? It can either help a plant grow, right? It can help us image a body, or that energy can simply just be communicating something to us, as is the case with sound or radio waves, all right? The applications, the number of ways that we use different kinds of waves, sound waves, electromagnetic waves, in the world is profound, and without using waves the way that we have, the world would look very different. And I hope after this chapter you guys really appreciate that. Okay, so some waves you may have heard of. What are these different kinds of waves, and what kind of energy do they transport? So on the top left corner here, you see a speaker. Obviously, those are sound waves. And what kind of energy are you really transporting there? You're really transporting the kinetic energy that make up molecules, right? So if I have a speaker that moves like this, you're actually knocking all the particles, the air particles that are next to it, and creating a compression in the air, and that compression will then hit the next layer of molecules, and on and on and on, like dominoes, and you have this kind of wave that's made up of compressions and low-density air, and then compressions and low-density air, and that series of compressions and low-density air wiggles your eardrum and allows you to hear stuff, okay? On the top right-hand corner, you have this very classic image of a prism, which is the cover of the legendary Pink Floyd album, Dark Side of the Moon. And you can guess that that's actually light waves, right? Or is actually electromagnetic radiation. We're going to talk about that later in the chapter, what that means. So, but light is really just visible electromagnetic radiation, visible oscillating electric and magnetic waves, okay? And they transport light energy, or electric and magnetic energy, okay? Water waves, on the lower left-hand image, they're transporting also kinetic energy of particles, right? These are actual particles that are moving. And then on the lower right, those are seismic waves, which also transport energy in the form of moving particles. But we're talking about very widespread moving particles within the Earth itself, okay? But just because the wave transports energy from one place to another doesn't mean it actually transports stuff. This is a very common misconception with waves. We think that a wave actually moves something like a water wave. We think is actually, if a water wave is out here cresting, then that same water wave is what actually lands on the beach, and that's not true. Really, what's happening is the wave is oscillating up and down, but the energy is propagating in the direction of the wave that we usually think that the wave is moving, right? So if you look at any given peak, right, of a wave on the water, really it's just moving up and down, okay? how do you know this? If anyone's surfed and they've sat out there and they've sat as waves pass underneath them, right? You notice that you just rise up and down, but you don't actually get taken with the wave until it actually breaks, and now you're kind of entwined with the surface of that wave. Okay? So misconception question number 1, consider a wave on a string as is shown in this picture. What is the direction of the velocity of a particle of string at point B? Well, remember, these individual points on a wave only move up and down, right? And if the wave is moving this way, as the slide says, then that means that the next part of the wave that B will experience will be the rising crest on this side. So that means B is going to rise, right? So at that point, the direction of the velocity of the particle at point B is going to be up because that crest is moving into B's position. All right? I hope that makes sense. In the next video, we're going to be discussing the anatomy of the wave. And here's where we start to talk about the nuts and bolts of what a wave is actually made of.